Okay, welcome to the third part of the Laplace transform lecture. So far we've defined the Laplace transform and we've used it to compute the Laplace transform of known functions, the exponential, sine and cosine. Now we want to go the other way and try to use it to compute an unknown function using rules for the Laplace transforms and the transforms known so far. So the first line here just states the definition of the transform and the LD law that we've seen repeatedly. And now let's see if we can solve this equation for f. So we know how its derivatives are related. We know its value at 0 and its derivative at 0. But we don't know what the function f is. And we would like to infer it. And we would like to do it using the Laplace transform. So remember, a few lectures back, we transformed this equation into power series and the coefficients, and then we computed the coefficients iteratively, step by step, and then we could approximate the function to a high degree near 0, but we couldn't really get the function expression itself. So here we actually can, at least for simple equations. So first step is to try to explore what the second derivative can be computed for, because we know the law for the first derivative. So let's start first by applying the LD law to the first derivative. We will need them in the next slide. So f prime here is the same as d of f. So if we write out this law, well, we don't really have to write out much, but let's do it anyway. So the Laplace for f prime, for this f prime at s, is equal to minus, well, f of 0 is 0, so minus 0 plus s times the Laplace transform of f at s, which is then just the 0 disappears, so it's s times LFS. And now we also have the second derivative. So what happens if we want to compute that? Well, we can use the same law, because the second derivative of s, that is the derivative of the first derivative at s. And then we can apply this law where the f is f prime. So this should be f prime and this should be f prime. So it's minus f prime at 0 plus s times L f prime s. And now we use our initial condition here. So this is equal to minus 1 plus s times, and well, we actually computed this one here to be s times LFS. So as that's s times, we actually get s squared times L f at s. So now we compute an expression for the first and second derivative in terms of the Laplace transform of the function without derivatives. And as usual, we also introduce the capital letter abbreviation. So let's use f for the Laplace transform of little f. And then if we sum this up, what we've computed so far is that actually we can abbreviate this one slightly further then. So it's s times f of s, and here it's equal to minus 1 plus s squared times f of s. It doesn't abbreviate that much, but in combination with this equation, we will get further. So let's move one step ahead and look at how we apply the Laplace transform to the whole equation. So if the equation holds, we can certainly apply every function we want to both sides and it will still hold. So in this case, we apply the Laplace transform to the left-hand side, applied to S, and the Laplace transform to the right-hand side, applied to S. Then we use linearity. So the Laplace transform of f double prime plus 2 times ends up being the Laplace transform that we computed on the previous page, plus 2 times the Laplace transform of f, and here it's 3 times the Laplace transform of s prime. And both the red and the blue underlined expressions we just computed. So let's remind ourselves briefly. The second derivative was minus 1 plus s squared f times s. So let's write that out. Minus 1 plus s squared. And actually I'd write f of s here directly. That's this blue term. And then it's 2 times f of s. And then remind ourselves here again, the other part was just s times f of s. So we have equal 3 times s times f of s. Okay, so now we have an equation which involves f of s, the capital F, not the lowercase anymore, and no derivatives. That's a much easier equation to solve than the equation from the start. So let's collect the terms here. How many f of s do we actually have? We have s squared of them, we have 2 of them, and we have, well, minus 3s of them if we move it over to the other side. So let's put that in a parenthesis. So we got s squared minus 3 times s plus 2, and parenthesis f of s. And at the same time, I'm moving this minus 1 over to the other side to become positive 1. Okay, so a polynomial times f of s equals 1. That means we can just divide both sides. So we found that the function capital F, so the Laplace transform of little f, is just 1 over s squared minus 3 times s plus 2. Okay, now for the next stage in this transformation, we need to factor this polynomial. We need to find the roots and write it as 2 factors, s minus s1 and s minus s2. And root finding is not what we're going to be practicing here, so I will just directly say, well, actually this is 1 over s minus 1 times s minus 2. We can use the PQ formula, for example, but we can at least check that it's reasonable. So the constant term in this multiplication will be minus 1 times minus 2, that's plus 2. Okay, that's fine. The second order term is just s times s, so that's s squared. And then we have 2 linear terms, minus s and minus 2s, combining to minus 3s. So we can at least verify it's correct. But in general, you will need to compute it. Now, if we would have been lucky and ended up at a function here, which we would recognize from our translation tables for Laplace transforms, then we would have been home. Then we would know what function little f is. But unfortunately, this is not visibly any of those functions. Fortunately, all of these rational functions can be simplified, or at least you can do a partial fraction decomposition. So you can actually write this in the form of a divided by s minus 1 plus b divided by s minus 2 for some a and b. But it's not obvious, I mean it's another theorem somewhere, but it's completely unrelated to the Laplace transform by itself. This is just something we would like to do. And why would we like to do it? We will infer a and b soon. We would like to do it because if this is the shape, then we recognize 1 over s minus 1 as the transform of the exponential function. And actually, this is also the transform of an exponential function. It's e to the power of 2t. So for whatever the coefficients are here, we can take a linear combination of a of the exponential and b of another exponential, and that will be the function little f, which will transform to this. So that's a good motivation for trying to find out what the capital A and capital B are. Okay, this was just some preparation. Yes, and I've already done this as well. Now, here is where I have some space for computing capital A and capital B. So now we have this sub-problem of trying to identify what A and B should be for the, I can make it blue, for this blue equation to hold. And one way to make that hold, I mean, it is to multiply both sides with what we've got below here, so that we get a simpler expression. So let's start with that. So then we get 1 equals A times s minus 2 plus b times s minus 1. So yeah, I multiply by this, and then the s minus 1 erases this term, so s minus 2 remains, and similarly here. So now we've got an equation which should hold. We could say, oh, there's just one equation, there's two unknowns, but this should hold for all s. So one way of solving it is to insert some arbitrary values of s, because this is a polynomial equation now. It's a polynomial equation of order 1, and then it's enough to have two distinct values of s, and then we can find the solution. And the simplest values to choose are actually 1 and 2. So let's do that. Let's take the s equals 1 case and the s equals 2 case. Okay, if s is equal to 1, we can write the equation again. It says 1 equals a times 1 minus 2 plus b times 1 minus 1. Well, this can be quite a lot simplified. A times 1 minus 2, that's minus a. And b times 1 minus 1, that's nothing. So actually, we have now got an equation between 1 and minus a. So this means, or actually is equivalent with saying that a is equal to minus 1. Okay, the next case, 1 is equal to a times 2 minus 2 plus b times 2 minus 1. I'm just substituting s with 2 in this equation. Okay, similarly, this can be quite a lot simplified. The first term is 0, the second term is b. So this means that actually b has to be positive 1. So what we've concluded is that yes, we can find a and b in this form, and actually we now have them. So this is minus 1 over s minus 1 plus 1 over s minus 2. Okay, and I'll shrink this part a bit. Because I want to now fill in the transformed equations. So, as I said before, we know that the Laplace transform of the exponential is 1 over s minus 1. That means that if we want to get minus 1 over s minus 1, we should just use the Laplace transform of minus the exponential. That would be minus 1 over s minus 1. Similarly, the Laplace transform of the function t to e to the power of 2t at s is going to be 1 over s minus 2. And that we computed a few slides back. And this doesn't even have another sign or a coefficient, so this is actually directly corresponding to this one. Then, using linearity, we can say, let f of t be minus e to the power of t plus, well, not 2, plus just e to the power of 2 times t. I'll just clean up that equality and minus sign to make it a little easier to read. So if we use this function for f, then this will transform to this part, this will transform to that part, and linearity says that the sum will transform to the whole expression. So this means now that this is supposedly the solution to our differential equation. But given that there were quite a few steps, one should always be very careful in checking it. So to check it, we need to check all the 3 requirements. This, and this. And you will not get full marks on the exam, because this is always a Laplace question on the exam if you don't check your result at the end. So do get into a habit of always checking it. So let's see here. F prime of t is, well, e to the power of t doesn't change. This becomes twice as big. Second derivative is still minus e to the power of t there, but here it's now up to 4 times e to the power of 2t. So the inner derivative is 2 in both times, so it becomes 2 and then 4. Sorry. Okay, so what do we need to check? Well, this equation, f of 0 equals 0. So let's check that first. It's a little tight on space here, but maybe I can create some space over to the left. So f of 0, that's minus e to the power of 0 plus e to the power of 0, which is minus 1 plus 1, which is 0. Yes. Okay, f prime at 0, that's minus e to the power of 0 plus 2 times e to the power of 0. So minus 1 plus 2 equals 1. That's also a yes. And now we just have to check the main equation. So then we have to compute the left-hand side and the right-hand side. So the left-hand side is the second derivative plus 2 times f. So the second derivative, oh, actually we can do it underneath here, so that's good. So the this is difficult to read. The left-hand side is, and then we can use that they're sort of lined up here. So how many e to the power of t do we have? Well, the second derivative contributes minus 1. So let's put it here, minus 1. And then 2 times this contributes minus 2. So it's minus 1 minus 2 times e to the power of t. Plus, okay, let's see how many we get from this other form. So first it's the second derivative, so that's 4. Plus, and then it's 2 times f, so 2 times this term. So that contributes 2 copies of e to the power of 2 times t. The right-hand side, on the other hand, well, the right-hand side is just 3 times f prime. So we can check here. So this 3 times, so this is minus 3 e to the power of t. And then 3 times plus 6 e to the power of 2t. And yes, minus 2, minus 1 minus 2 is minus 3, 4 plus 2 is 6. So the left-hand side equals the right-hand side for all t. Good. So we've managed to use the differential equation plus the LD rule and partial fraction decomposition to solve for f from an unknown f here. And we got the result that it's actually this function. For all t, it's defined. And this was just some preliminary material. So the summary here, we find a transform which goes roughly from R to R to C. I say roughly because not all functions are allowed, and it's not all the arguments allowed here. So we have to make sure that the limit at infinity vanishes. It's defined as this integral, but we rarely use the definition. We almost always use its properties, and most commonly the LD rule, the Laplace derivative rule. And we've managed to compute some Laplace transforms and shown the steps you have to take to infer the function from a differential equation of a reasonably simple form yourself. So those steps are: first, apply the transform to your ordinary differential equation. Simplify using linearity. Simplify using the LD rule. And if you've done that correctly, you will have a rational expression. Rational meaning a quotient of polynomials. So you will actually have an expression for the transform of the function without any derivatives or anything. It's just a transform and it's a rational expression. Then you do partial fraction decomposition to express that rational expression in a sum of simpler terms. And then you transform back by what I call here pattern matching. So you look for example, this pattern, or the pattern for sine or cosine. And if you manage to find those patterns, well, combined with the linear combinations, then you can be reasonably sure that you have transformed back to the correct expression. And then the red box here says check. Always, when you've done all these transformations, there is a high risk of making a sign mistake, or forgetting a number, or reading a 2 as a 3 or something like that. So do check all the 3 parts, or the 2 if it's a simple equation. Check the equation and the initial conditions at its end. Okay, that was all for this part.